Good morning and good afternoon, everybody. So today we are hosting ASEG Webinar series. Uh, Thanks to all our speakers and especially Sumit today joining from Texas, far away from Australia. So we'll go through some of the housekeeping slides, which is about today's talk, what ASEG does, and its some of its members benefit, and like any of the upcoming talks also. And good thing is these talks we are recording in YouTube, so anytime you can go back and watch them. So welcome all. Today's talk is hosted by Western Australia branch, delivered by Dr. Sumit Verma, assistant professor, University of Texas Permian Basin. So talk title is Seismic Attribute Illumination of Complex Fault Network North Slope, Alaska. So who is working in the seismic area for interpretation, and they have quite interesting outcome from this talk. So we need to thank our corporate sponsor. Without them, running society is always difficult. So these are corporate sponsors. Thanks to them. Main corporate plus is HISIS, Total Seismic and Velsis. And some of our corporate sponsors are Archimedes Financial Planning, GDD, Southern Geoscience, as well as Santos. So thanks them again for supporting ASEG for several years, and presently we are in the 50th anniversary of the ASEG this year. We also have our branch sponsor specific to the each state and territory. So we have left hand side, we have South Australia Northern Territory sponsor, we have Western Australia branch sponsor, as well as New South Wales sponsor. So thanks all of the branch sponsor also, because they are helping to host regular events, face-to-face events. This year it's a less opportunity because of that pandemic, but as soon as situation go back, we'll host some of those face-to-face talk as well. Some of the housekeeping and Zoom explanation. So here mostly we have a question answer button here. If you hover over your control panel and click on that question answer session, then you can let the moderator know you have a question, and then I'll pass on that question to Sumit for answering. Following that, within the specified time, if you still have question, we can take those questions offline and probably contact Sumit and get back to you. So here basically all participants will attend, but they cannot, we have muted all of them forcefully so that no one can jump in at the time of talk. And at the end of this talk, we probably take those questions and session. So these are some of our upcoming talks, which is again still happening through webinars. So next month, July 7th, David Annetts of CSIRO will speak about 10 years in the wild, the P223 experiment. Second, we have a mentoring workshop kinds webinar given by Marina Costello, and it will be quite interesting. It's happening on 14th July. Followed by 15th July, we have another talk on computation methods in geophysics by Indrajit Rai. And then we have 23rd July, Mujtaba Rajabi will speak about contemporary crustal stress pattern of Australia. So these are the upcoming talks. I think all the members will receive a link for register. So if anyone have interest on the specific topic, you can join in. Some of the members benefit of the ASEG, what we does and how the members benefit from our membership. So basically free access to Exploration Geophysics Journal, published high quality research result and case studies. It is happening for a long time. And then we have a free copy to the preview, which is basically released bi-monthly magazine as like what are the events happening, regular up-to-date information normally given in preview. Also, ASEG collaborate with other society and organize every 2 years a conference, AEGC conference. They'll get some reduced entry. Whoever the member of ASEG want to join that conference. As well as we have a free entry for the regular technical events in the specific state, depending upon the normally some branch does in first week, some in second week, but it's normally pretty good time to join those regular talks. We have access to job advertisement posted on the ASEG's original website, which is you can see www.aseg.org, as well as they provide some annual wine offer. I think a lot of people already have taken that benefit. Then we have our social events like any kind of either mentoring event or maybe get together events will normally happen like that, as well as the professional networking events, which is normally done through these regular technical events, which we have a session to interact with each other. And finally, not the end. So ASEG supports research funding. So every year they funded 2 or 3 projects, as well as they provide some scholarship for each of the branch specific. But research funding is for all over the FedEx territory, like all over the Australia. And the students here get all free membership and half price for retirees and recent graduates. So these are the good benefits of ASEG. I'm going to the next slides, which is about our presence in the social media, because it is need of the hour. Everyone checking those platforms. So we have the original ASEG events normally hosted in our website. Then we have Facebook account, Twitter news, as well as LinkedIn and ASEG videos. And all these talks will be uploaded in the ASEG videos, which is happening this year. So it will be really benefited for the other members who cannot join in that exact time. So now coming back to this today's talk, it's would be quite interesting. From the intro slide, you can see it. So topic is seismic attribute illumination of complex fault network slope of Alaska region. So given by Sumit Verma, he joined from Texas, and let me give you some brief intro about him. So let me read through it. So he is the assistant professor of geophysics at the University of Texas Permian Basin. Before that, he received his master's in applied geophysics from Indian School of Mines, Dhanbad, and PhD from University of Oklahoma in 2015. After earning his PhD, he has worked as a postdoctoral research fellow at University of Wyoming. Before that, he actually also worked as a 4 years in development geophysics. So industry-wise work, 2007 to 2011, within the Reliance Industries Limited back in India. His main research interest is seismic interpretation, quantitative interpretation, as well as reservoir characterization. He is also a deputy editor for the peer-reviewed scientific journal Interpretation. So you may have seen already on that journal as in the editorial page. With that, I'll pass on to Sumit, and summary of the talk is already shared all of you guys. So I'm not going to read through it. So hopefully you're going to enjoy it. Thank you, Sumit. Now back to you.
Thanks a lot, Partha. Thank you so much. So I will share my screen here. And I hope you all can see my screen now. So thank you so much, Partha, for introducing me and giving me an opportunity to present here in Australian Society of Exploration Geophysics. So my talk is on seismic attribute illumination of complex fault network in North Slope, Alaska. This work actually was conducted in collaboration from, say, University of Alaska, Shubhajit Bhattacharya, and me at University of Texas Permian Basin. we collaborated to work on, say, illuminating some type of fault. So that's what the presentation title says, right? So we will see how we are doing it, and I hope everyone finds it interesting. So actually in the this region, North Slope, Alaska, there are many deep reservoirs which are fault controlled. And there has been a different series of tectonic events that has taken place and that has caused it. And say when there are faults and fractures present, then they can be either a hindrance or a help for say hydrocarbon production. So for example, they can be say migration pathways, and then the hydrocarbon can flow from the source rock to the reservoir rock, and you can see it as a benefit for us. But then it can also be like if the fault is breaking the seal off and the hydrocarbons is moving away, so it can be a hindrance as well. And in our case here, there is a compartmentalization of reservoir that can also happen through the presence of a series of faults. So in this talk, though, we will talk about, say, some strain illuminating attributes, including, say, aberrancy and curvature, which will help us to identify faults and then find out the relative ages of the fault. And we will further investigate the influence of the deeper structure on creating these shallow sedimentary faults, and then how that influences the overall, say, deposition later on. Yeah. So the area here is very close to Prudhoe Bay, which is probably everyone is familiar with. It's one of the biggest oil and gas field in the United States, and there are Kuparuk and Line Point. So Storms 3D, this is our study area. It's very close to that. And here, actually, I wanted to give a perspective for all the people in Australia to see like where actually this Alaska region is located. If I'm pretty sure that everyone knows about that, but that's just to give it a view that this is not too far from your homeland. Okay, so here further on, so there are different mega sequences here. So there is like a Franklinian and Ellesmerian Beaufortian and Brookian. So I will actually talk a little bit about that here. Say the Franklinian was the time when the basement fabric was taken place. So all the initial tectonic fabric was formed at this time. And then further on, Ellesmerian, which is actually dominated by rifting event. And in this time, it's kind of a passive margin time, and rifting is taking place. And Shublik Shale was deposited at this time. Shublik Shale is of our interest. That is the formation that I'm going to talk about. And it's say Triassic formation. It has been considered as a source rock, or I mean, it has been it is a source rock for different producing formations, as well as it is considered unconventional resource play for some time. But there has been like say no not a really big move in that direction so far, but in future, when the economics is right, it might happen. So further, so here, this is a vertical seismic section that you see here, A to B, and that is shown here. This is the Shublik time structure map here. So you can see I have marked few arrows here. So this arrow here shows that actually there is a fault here. And then if you see at the same location here, you can see the big change in color. So there is a fault here and which has a significant throw. Okay, so you can see that. And then there is this fault here, one more. You can also see that is a fault, like a break in reflector. But I mean, this one has a higher throw. Both of them are normal faults. Further on, I mean, you see these purple arrows, and they are also representing some kind of, say, dip in the this reflector. So they might be faults, we do not know. And then you on the map though, you see some kind of these crisscross patterns. And at those locations, we do not see like so many things. So we will try to zoom in into this to understand it better. So let's see at this location. You can see there is a fault here, clear fault with some displacement. And then let's zoom into this one. You can see a little bit more clear flexure. And further on, in this the third location here, this box, we do see a little bit of flexure, but not too much. But this is showing some kind of crisscross pattern. So we will try to follow that with further in our further slides. Okay. So here I try to divide it into three types of structures that we see here. So one is the number one that is showing us a very significant amount of throw, and then we can see it on the seismic. And the second one is there is a insignificant but very clear visible flexure on the seismic. You can see that there is a little bit of movement down. Okay, but the third one is very slight change, which hardly visible actually here. So very weak flexure. So this would be called actually a subseismic fault if you have to classify that as a subseismic or seismic. Okay, so here I will utilize say three attributes: coherence, curvature, and aberrancy for trying to study these faults and fractures. So coming to coherence, actually probably most of the people know about coherence attribute. It has been there since quite a long time. I mean, there can be different estimates of coherence. The coherence is basically an algorithm in which you are trying to compare say the trace which is on target with the adjacent traces, and then try to find how much it correlates to the other traces. Okay, so there can be different estimates of coherence. It's trying to actually compare here waveform. So there can be different algorithms and different window sizes and the window lengths. So here I'm showing you 5 traces being compared with the middle trace here. And say in our case, we have used Eigenstructure estimate of coherence. So let's see how that is calculated. So in order to calculate the Eigenstructure as coherence, we first of all, we try to say get a window aligned with the reflector dip. We can do that if we have a dip volume of the data. So that's how in ASPE we calculate all those attributes. So now as the window is aligned here, I can now calculate actually the total energy of the traces by just say squaring all these traces and then say adding all these things up. Say there are 5 traces here, and suppose there is 5 samples up, 5 samples below. So total of 11 samples here. So this will be 55 samples in this thing. So square that, and then I can calculate a wavelet that best fits the data. Okay, so this is some kind of say eigenstructure or principal component part of it. So now it is computed, and then we compute a scaling factor for each of these and then try to fit it on all of these traces. And then that will be actually the coherent component for that trace. And this is also known well by processing people. They call it the Carhoonen-Love filter, or sometimes you may hear principal component analysis or eigenvector or eigenvalue decomposition. So this is the first principal component of the data. And further on, you calculate the energy of these components by, say, squaring it. And then now you just take a ratio of energy of the coherent component of the data and the input energy. So it's basically the coherent energy divided by the total energy here. And that gives you the coherence. So let's look at the result here. So here, if you see, this is the coherence computed on the data. And I have extracted it along the Shublik top surface where you seeing all those faults and all. So here you can see a little bit of indication of this fault and a little bit of this fault. And then maybe if you have a very good eye, maybe you can see this one and this one. Further on, you do not see much here. Okay, so this is 0 to 1 scale. So about coherence, sometimes you have to change the scale of coherence and then try to look into the more narrow band of coherence. So you try to change, I try to change that, and then here 0.95 to 1. It's very narrow band, actually, very narrow band of coherence that I'm looking at. But I see a little bit better these things. This one is for sure, like I can see it really clearly, this fault here. So type 1 is detected. Type 2 is also actually seen fine. Type 3, actually, it's a little bit more challenging actually to see here any fault here. And when you are trying to narrow these band of coherence, then like if there is any kind of noise existing in the data, that will also enhance at that point. So that prohibits us from seeing anything. So we'll move further on and then go to the second attribute and try to understand what is this curvature and how we can compute it. So here, curvature in through 2D, we can define it easily. Like say this is a curved surface here. So if you have to compute the curvature for this surface, you have to draw, say, a circle on the bottom and then find out the radius of that. And then if you take the inverse of the radius, then that will give you the value of curvature. So as a convention, if you draw the circle below this curve, that will be considered a positive curvature. Whereas if you draw the circle on the top, that will be considered a negative curvature. And I mean, based on this radius of the thing, you can also already see that if this is a flat plane, that will require an infinite radius circle to be fit here. And that makes the curvature here 0. And if there is a constant depth, this similar to this, that the case will be the same. It will have 0 curvature. But then if there is a change in curvature, a change in depth, then you will see the curvature there. Okay. So this is in 2D. One more thing, just to point out that the anticlines will have a positive curvature and the synclines will have a negative curvature. So in order to define a 3D body or represent a 3D body, you might need 2 curvature actually, rather than just 1 curvature. Like in 2D, you just need 1 curvature. So here in 3 dimension, we define the 2 curvature as K1 most positive principal curvature and K2 most negative principal curvature. So the most positive principal curvature, again, it's the highest value of curvature, irrespective of its sign, actually. So it's the most positive curvature value. And K2 is the most negative, irrespective of the sign. So here for a bowl, both curvature actually are going to be negative. So the one which has a higher negative value is our K2 here, and K1 will be a slightly lesser value. And for a valley, though the most negative curvature will show a magnitude-wise higher value, but the K1 will be 0. That is along this thing. So you are trying to draw a circle, which is say the smaller circle has the bigger curvature. So that's the idea here. Similarly, here for this ridge, suppose you have to draw a circle. So for this one, the K1 most positive curvature has anomalous value, high value. The K2 values will be 0. Okay. Similarly, the other geometry features can be seen here. Okay. So now most negative curvature computed on our data set. This is again computed in actually volumetric sense, and then we are extracting the values of most negative curvature along the Shublik top horizon. And here you can see this fault here, right? And here you can also see this fault. You can see this fault. These faults, which were not visible so much in the other attribute coherence, here you can see them more clearly. So now, I mean, this one is both detected. This one is also detected. Okay. So this is most negative curvature. This is our magnitude of curvature. Now further, if we want to use the strike of curvature, you might see a little bit more clear things here. What does it show here? It's showing you the direction in which these lineations are. So for example, this lineation that you see for one of the faults, like say for this fault that you are seeing more purple color. So purple is like, say, it's aligned in that direction. So that is the strike of the curvature. Okay. And you can also see the yellow one. So the yellow one is like this here, and then the blue one like this direction. So it's basically the same direction as it's showing here. So it's showing you the strike of the curvature, how it's striking, the most negative curvature. So it gives you a little better idea if you want to see the picture and then see, okay, which direction and how the directions are changing. So it's more clear. How do we do it? So we are combining the two attributes, the strike, K2 strike, and then K2 magnitude. So I'm trying to show only the areas where the K2 magnitude has high positive values, and not show the negative values here. Okay. So that's how I'm trying to do it here. Okay. So further on, so this is the concept of aberrancy attributes. This is one of the new attribute called aberrancy. I will take a little bit of time here to describe this attribute, because I'm not sure that everyone is familiar about this attribute, because this is very recent attribute. So this is basically the third derivative of the surface, but I'll show you it in this process of showing this monocline here. There is this monocline. And if you take the first derivative of this structure, you will find the dip. And the dip is changing in this way here for this monocline. So further on, if you want to compute the curvature, you will find that the positive side here, you can fit the circle here, and then you can fit a circle on the top. So positive curvature and negative curvature. So that's how we are doing it here. And then further on top of this, if you take another derivative, that will be our aberrancy. Okay. And the azimuth of aberrancy can be also calculated, and then that will be showing you the direction of the trough or the down thrown side. Okay. here. So as if you are a mathematician, you might think like there will be, I guess, three roots for if there is a third order equation, third order partial differential equation, right? So you would have three roots. So this is actually a total aberrancy uh, magnitude and total aberrancy azimuth. It's not just like say one of those. Is the total. They are added all. Okay. So here, if you want to see how we represent, how we use this aberrancy. So here, say for example, there is this sink. So I'm trying to show you how we can utilize the total aberrancy uh, azimuth and total aberrancy magnitude. So here we will try to combine these two attributes together. So we will try to get it like wherever there is high values of aberrancy, we will try to show the aberrancy azimuth in that area. So here, for example, for this one, so you can see this is our sink, and then the azimuth here is going to show you the direction in which there is trough. So if you are suppose going from say the east direction, the dip is in the west, so it will show the color of west. So that is the azimuth is showing, and it's just showing at these places because that's where aberrancy magnitude is high, and then that's the area we are trying to show the aberrancy azimuth. Okay. So similarly, I mean, you can see like from this direction if you go, so you will hit the trough if you go north. Okay. So here, this is total aberrancy magnitude. Here you can see those faults more actually clearly here in this aberrancy magnitude. Here these faults, but I mean it's also although it's clear, but we'll try to see. And now if we use aberrancy azimuth along with the magnitude, how does it show up? So here you can see, say now you can see all these lineations more clearly. So you can see that, say that there is this lineation going this way and this lineation going this way. These are for the faults which had very small amount of throw. So the other faults, this one and this one, are already very clear actually. So let's try to analyze this data. And further, one more thing here, like I mean, you can see that along the fault, you can see in both directions if you go how that will change. So if it is kind of making a valley shape or a shape of kind of anticline, you can also get it from here. If the two directions are towards each other, then you can see if it's a valley or if it is an anticline. So now, so we will try to analyze the results that we have received from curvature and aberrancy, and try to understand, can we find out something about the relative edges of the structures, and also if we can have some information on the possible cause of the generation of these structures. Okay, so let's look at that. So there are some different structural geology principles that we can use. One is like, say, we can use the fault orientations. So if the fault orientation here, you can see the fault orientation is saying that we have one orientation like this, and that is like this magenta one. And there is another orientation, the yellow one here like this. And then there is a blue orientation. So there are three orientations only. We had divided the faults into three types. One very significant throw, and then insignificant, less significant throw, and then almost no throw. or barely having a flexure. So here it looks like a little bit different situation now on this plot. So you can see that this magenta actually is matching the two directions here, here, here. These are all matching. So probably the, these all these faults may be genetically related to each other. So we will actually call it the magenta fault from here onwards to the end of my presentation. And we divide the things which were looking like very tiny flexures earlier as like say yellow lineations and the blue lineations. So and we think that they might be of different origins, or they might be conjugate. So there's one more thing though here. Say these two lineations, they are at approximately 90-degree angles. So if they were to be conjugate faults, it might be a little bit more challenging as per the structural geology concepts. If you see the more conjugate faults are like say they can form at more like say 60, 120 degrees, not the 90-degree formation of say conjugate faults is more challenging. Okay. So further on, say cross-cutting relationships. So cross-cutting relationships suggests that say the younger fault will cut across the older fault. So it will cut across this say here we can see that kind of examples quite a bit. Here you can see say so in this part actually you can see some of these faults, the blue faults are cutting across this magenta fault. So there is a clear relationship that these faults, these ones, are actually younger than these magenta faults. You can see it in different places here, the same relationship happening. Further on, there is another principle. It's called single tip abutting. So when there is an older fault, the younger fault might terminate against this older fault and then not further from here. Just stop it there. And then we can see that here in different places actually, the fault going there and then just stopping and then not continuing. So here, for example, you can see some of these things like this one coming from here, stopping, and then this fault is going from here and stopping, fault is coming here, stopping. So the yellow and the blue faults are stopping against this fault. So these two are younger. Okay, and double tip abutting, that also is very similar concept as single tip abutting. There like say the fault, this older fault is bounding this younger fault section. Okay. That's happening, say somewhat like that here in this area. You can see that quite clearly actually, and then from here to here as well. So further on now, actually coming to trying to explain what's happening here. There is a student in University of Alaska. He worked on this project trying to figure out how this is happening. So he tried to mark different faults, like where he's seeing the fault. So he's saying that we can see this fault, the magenta one, from here to here. And the blue one is from here to here, this section, this one. And the yellow one is from here to here. So actually this fault here is the basement fault. It's like the basement is faulted once, and then there are some reactivation of those faults in later times. This fault is getting reactivated. And this fault probably formed at this time, and then this fault formed at this time. So that's why they are looking like this. But how exactly it's happening? Actually, say there is the example from Bonaparte Basin in north-west shelf of Australia, where similar kind of pattern has been seen. So what has happened is there are these pre-existing structures, and on that there is an extension in the oblique direction. So that causes the N echelon faulting. So that's why these faults are getting created, and then for some reason they are at these 90 degrees to each other, but they are created at by different events, and then both are created by, say, having an oblique extension to the pre-existing structure. So now, actually, yeah, here I try to put it into words. So here, the Big Throw Magenta fault here, the faulting was deactivated several times. The Shublik faulting occurred in late Jurassic. That's why you see a mark here. And the insignificant throw, the blue fault, that is generated due to the oblique reactivation of underlying Jurassic-aged faults. And that resulted in NH1 faulting, and that happened, say, in early Cretaceous and Rift. And then the insignificant yellow fault, this one, so that is oblique reactivation underlying Jurassic-aged faults. And that was probably in Eocene as post-Rift fault. Further on, so in my conclusions here, the coherence was not so useful for this study when we are trying to find out, like, say, the very small amount of offset. There is no waveform change across the fault, so that causes not get any offset. Curvature and aberrancy illuminates the complex faults here quite well. Curvature provides like the strike of the fault when we use the strike of the curvature. And together, curvature and aberrancy can help find the relative edges of the faults. Extension in oblique direction to the pre-existing structure can result in an echelon segmented younger faults. Okay, so I would like to thank Alaska Department of Natural Resources, Division of Oil and Gas. So they had provided this tax credit data. In fact, anyone can obtain it. The universities can obtain it, I guess, in the United States. And ASPI software was used. So this is ASPI consortium symbol, and all the attributes were from here. I'm part of this ASPI consortium. And Petrel was used for seismic interpretation, and Icon Science Rock Talk was used for belt seismic time. And further, thank you all at, say, Australian Society of Exploration Geophysics for listening to my talk and giving me an opportunity to present my work. Thank you. I will take questions if there is any. So over to Partha.
Thank you very much for this nice talk. Now probably we'll take some question answer, if anything have.
I think it takes a bit to get the questions.
So So if anyone have any question, you can type it through that question answer section. If you hover around your control panel, the Zoom, then you probably see there is a question answer button. You can type in there.
Okay, so I got a question. So the question says, good talk. Did you try analyzing shallower horizons? And if so, how did you handle the acquisition footprint? So, okay. So I uh, we had seen the shallower horizons, but for say to answer this question for how can we handle the acquisition footprint, that is a question, then I mean you can apply say a KX-KY filter, so that can work well for the post-tag data if you are working with the post-tag. But then if you have the pre-stack data, then you can apply, say, your structure-oriented filters can also remove your acquisition footprints. So, but I had not tried on this data the acquisition footprint. Am I right? Because no, I did not try on this data set. But in general, I tried that. In this data set, I think it was okay since the beginning for this level, and then I for the shallower level, those footprints are more severe. So if you are trying to work with the shallower sections, then you might have to apply the acquisition footprint suppression algorithms, and better luck with removing that if you have the pre-stack data. So
Before anyone ask any question, I have one question.
sure, yeah.
So this some of the fault we can see clearly from this throw pattern, like where we see very small throw, like that crisscross pattern. Because I have worked in one project, we see this kind of fault, and during the seismic interpretation and processing, but we could not answer why like this crisscross pattern is changing. So probably it's a more of interpretation type, like yellow and blue faults. You are saying that. So what could be the possible reason that there should not have any artifacts is generated from seismic, that possibility which will show this crisscross pattern?
Oh, okay. Because one, it is not happening in the whole section. Okay, so it is we did not see in the whole thing. Like say so one like say for example, if like since Todd here has mentioned about say footprints. So footprints will be happening in your inline and crossline directions. So this is not in an inline and crossline direction. So you can think that okay, these are not like the typical. It cannot happen as a acquisition footprint like that. And besides that, you see some of these patterns, like say this direction is only visible. Say the blue one is just from this to this section, but the yellow one is from this to this section. And they are very consistent actually. So that's why we think it's more geologic, not anything to do with the artifacts.
Thank you.
Yeah.
Maybe we can wait another 5-10 minutes before I closing it out.
Yeah.
We just ask another question, like
Yeah,
because
sure.
this kind of very complex network of fault is uh, in the US, because unconventional is quite active there. Have you seen
Uh-huh.
that this kind of complex fault people analyze before doing horizontal drilling or targeting their zone? Like,
Yes, yes, actually, that is a very good question because when you have such kind of faults, in fact, these faults are very tiny. So, but when you see, like, say, the production of unconventional depends on how much permeability you have. So it might actually, in some cases, help. These faults might provide you more fractures around them. And then that can actually help enhance your production. At the same time, there is a risk that if there is, say, suppose the fractures are present like that, that these are in fact actually tiny faults, and then that also says that there will be a lot of fractures, probably the same direction. So you want to plan your wells according to your this is the stress, like fracture patterns like this, to maximize your production. So they are quite critical, in fact, for unconventionals.
yes, means we see like some of risk analysis or the microseismicities, they report the like some of the faults when they have drilled may have not seen it, and when
Mhm.
they're going for a like continuous horizontal drilling, and some of the
Mhm.
fractures or fault natural fractures, they hit it, and then it causes some kind of microseismicity. But I don't think every basin have that kind of data quality and things where they have analyzed properly how that
Yeah,
fault
the
pattern is.
data quality here is decent actually.
Yeah.
Although this is an onshore stuff, but it is quite good. I mean, more recent data, in fact. So, I mean, I worked with a lot of older data in Texas, so
Yeah.
compared with that, it's really pretty. Yeah, it's a very good question. So, any other question coming?
Don't think there is any more question. But all these things will be recorded there. So if anyone have any question later on, reach to ASEG, probably we can pass on to you to answer
Yeah,
those questions.
yeah, that will be great. That will
Yeah.
be great. Yeah.
So thank you very much again for joining. It is already night time there, because of the time difference. But we have able to make it. So thank you very much again from the ASEC for giving us a talk in a completely
Thank you so
different
much, Partha,
perspective.
for inviting me.
So with that, we maybe close this session and talk to you later.
Okay, thank you.
Bye.